Okay, so this is Modular 7, The Power of the Story. This story is Dr. Rittner, The Human Cannonball, by Norman Crowe from the University of Central Oklahoma, ESFR 5203, Advanced Educational Psychology. Our goal here is to determine if Dr. Rittner can shoot herself from a cannon at the Chesapeake Energy Arena. Dr. Rittner, when not teaching and grading assignments for her students, she actually has a secret life. Tapping into her love of physics and her sense of adventure, she's decided to become the Oklahoma City Human Cannonball. She normally conducts her act in the outside, but due to her rising popularity, she's been asked to perform at the halftime performance for the Oklahoma City Thunder at the Chesapeake Energy Arena. In here, we got our four C's, the first being causality, which in this case is a law of physics. We are solving problems for forces in two dimensions, and the cause here is physics. Newton gives us our first law of motion, which is an object in motion stays in motion, and an object in rest stays at rest unless acted upon by an outside force. In this case, there are two forces. The initial movement of Dr. Rittner, as she is dramatically shot out of a cannon, and the second force is the downward force due to gravity. The second C is conflict. In this story, the conflict is the safety of Dr. Rittner. She does have a lot of assignments that are assigned for her classes, but the assignments are good for us. So we really do want her to return from spring break safe. The third C is complications. In this story, the complications are the danger associated with the stunt. Slamming into the roof or missing the landing pad is a very big complication. Physics says that two objects cannot occupy the same space at the same time. As we move forward in this class, we'll talk about momentum, collisions, and energy, but for now, we don't need to know the mathematics behind hitting the roof or missing the pad to know that doing so is a very bad thing. Will she land on the pad? Will she stay below the roof of the arena? Only our understanding of physics and accurate computational procedures will keep Dr. Rittner safe. Finally, our fourth C is character. In this, we have two characters. The first being Dr. Rittner, and of course the next one being the laws of physics. The arena presents us with some constrictions that we must adhere to. The floor of the arena is 143 feet long. The distance from the arena event level floor to the bottom of the steel roof trusses is 130 feet. The cannon will launch Dr. Rittner at a velocity of 60 miles per hour at an angle of 72 degrees above the horizon. The first thing we need to determine is how far away will the landing bag need to be placed from the edge of the cannon. This is denoted by distance d. The next thing we need to know is how high above the cannon will Dr. Rittner reach as she follows the path of her trajectory. This is denoted by a height of h. Finally, is this performance even possible inside this venue? Remember, we need to think about the roof and the edge of the arena. Will Dr. Rittner travel too high and strike the roof of the arena? And if not, will Dr. Rittner travel too far and crash into the wall of the arena? So looking at our tree diagram, we can organize this lesson further and introduce forces in two dimensions. This is comprised of two main areas: horizontally launched projectiles and non-horizontally launched projectiles. Since we're launching our teacher at an angle, we are dealing with non-horizontally launched projectiles. Our first step will be to analyze the problem and identify specified information and determine implied information by modeling how we walk through the problem. Then we will isolate what needs to be solved. Finally, we will utilize previously learned information such as dimensional analysis, Newton's first law of motion, and kinematic equations, along with 2D force concepts to determine unknown data. The bottom line is, will Dr. Rittner survive? Meaning will be created by connecting new learning to previous learning. In this case, we rely on Newton's first law of motion, use of dimensional analysis to convert imperial to metric, and kinematic equations to solve this problem. All of these were previously learned. We will also connect new learning to students' backgrounds at a personal level. In this case, we rely on Newton's first law of motion, correction. We know that students have always wanted to launch a teacher out of a cannon. The question is, can we do it safely? Can we do something extraordinary while keeping our teacher safe? This makes a connection to the student at the personal level. Next, we will model how the skill or concept is used. With demonstrations, think aloud, self-talks, and modeling, students see the useful application of what is being taught. Finding specified information, such as the angle of launch and the initial velocity, selecting the correct kinematic formula, identifying implied information, such as the acceleration due to the force of gravity, separating the components of the vector into vertical and horizontal components, and transferring information common in each component is talked through. Finally, demonstrating real-world relevancy. Here we weave relevancy with curriculum integration. Algebra and trigonometry is used to show how real-world problems are solved using the laws of physics and mathematics. Transfer is created by providing a memorable example of how forces in 2 dimensions are used in the real world, asking students to provide examples of problems that can be used in other areas. To go further, provided some of these examples are good, they could be used as homework, bell ringers, or on exams. We can also use gamification to show use of the information in games such as Angry Bird. It'd be kind of hard to come home from school and tell your parents that your homework is to play 7 levels of Angry Bird. Next, and finally, we'll assess physics concepts. We need to place less weight on the memorization of the equations or focusing on mathematical mistakes, but really focus on the application of the concepts, selecting the correct equation to use, and the process it takes to solve the problem. So thank you. That is my story. The question here now is, did Dr. Rittner actually survive her launch from a cannon? You'll have to use physics to find out.